And welcome back. Our next talk is AADL Modeling and Analysis Tool for Cyber Resiliency, GE Verdict / DARPA case by Michael Durling. Michael is the technical manager for high assurance systems at General Electric Research. He has been at GRC since 1999 in various engineering leadership roles. Michael, welcome to AADL User Days. Take it away.
Thank you, Shane. Hi, I'm Mike Durling. I'm going to talk about a tool that we developed on a DARPA program. The G research team, along with a cyber analyst from our aviation systems business unit and colleagues from the University of Iowa, developed this tool that I'll be talking about today. The way the pitch will go today is first I'll introduce the DARPA case program, give you a little background of what the program was intending to create. I'll talk a little bit about our VERDICT tool, and then I'll go through a working example and show a little bit of hands-on how to use the tool. Then I'll show you our GitHub where the tool is available, along with some models that you can use and some training material on our wiki, and then point to some publications and then take some questions. So the DARPA case program was a program created by Ray Richards, Cyber Assured Systems Engineering. And the idea here was to develop tools that would enable a system engineer to do modeling and analysis of cyber resiliency at design time. So if you think about, there's all kinds of tools to do safety analysis or performance analysis or reliability analysis. And the aim of this program was really to develop tools to be able to model and analyze for cyber resiliency. So VERDICT stands for Verification Evidence and Resilient Design in Anticipation of Cybersecurity Threats. And the objectives of our VERDICT program were to develop this open source tool that could be used by systems engineers to create models and then do an architecture synthesis function that would be able to identify cyber vulnerabilities and generate a set of recommended defenses and the level of the defenses in order to satisfy the cyber vulnerabilities given the mission and consequence. That's the first major functionality of the tool. The second big function is a cyber resiliency verifier. And that's a formal proof of cyber properties that are annotated in the model against behavioral model captured in agree. So that's really more of a formal analysis tool. So there's an architectural analysis tool and then a formal proof-based analysis tool. So some of the innovations were synthesis of cyber resilient architecture that really considers mission, safety, and security. So when we do our design, we call out the intended missions for the architecture, and we capture cyber and safety requirements. And then the tool will generate a fault tree with a reliability score and an attack defense tree with a likelihood of successful attack. We'll localize feedback to components and highlight where the components are vulnerable and make recommendations that are local to components. It's very automated, so the system engineer doesn't really need to be a cyber expert. They need to understand the architecture of the system that they're building. And with the cyber resiliency verifier, will help us reason about future attacks. So the expected impact is it's really to help system engineers at design time and give them clear, actionable information. It should improve the cyber resiliency of military and critical infrastructure systems, and provide an open source resource tool along with documentation and examples for the community to use. Based on time today, I'm really only going to discuss the model-based architecture synthesis piece. But if you want more information about the Cyber Resiliency Verifier, again, we have a GitHub that I'll point you to later in the presentation. So this is a chart I share if I'm reintroducing the tool at a high level to folks. And basically at GE, we're interested in aircraft engines, avionics. On the program, we were working on a weapons system. You start with the architecture and some of the requirements of the system. And then we capture an architecture model in AADL. I point people at this AADL reference for folks who aren't familiar with AADL, and let them know that it's a language used to capture models at the architectural level for embedded systems developed by SEI. We use the OSADI tool to edit the AADL. And we model processors, buses, the software architecture, all the major embedded system components. And we were concerned with all the IO and the data flow throughout the model. When we look at VERDICT, you see it through this OSADI environment. And we capture our model in a text-based AADL, and then we can generate diagrams like you see in the picture here that shows the major components of the system and the connections between them. And then there's user feedback that the user can see through the environment there. So our VERDICT tool is actually a plugin to OSADI. So after the system engineer creates their model, they call VERDICT from the plugin menu, and the tool will provide feedback in terms of KPEC vulnerability. So for the components and the connections that the system engineer provided, when we run the VERDICT tool in the model-based architecture analysis mode, it will say this particular component is vulnerable to these particular KPECs. Further, it will recommend defenses based on NIST 800-53 defenses. So we tried to use language common to the industry so that when we provided feedback of risks and recommendations for defenses, it was interpretable and understandable and recognized by the overall community. So inside the tool, we can adjust the strength of the defenses that we're recommending and essentially run the tool until we pass the cyber resiliency that we're looking for. And then we can say that the system with our recommendations would be cyber resilient. So let's jump into, so before case, when we talk to our cyber analysis systems engineer at the business, referred to cyber analysis as being labor intensive, time consuming, separate from the systems modeling and safety analysis process. There's groups or teams that take care of each of those functions, and the cyber analysis was separate from that. Wasn't really threat or mission based. Really a process assurance step. And now with the tool, there's a lot more automation. There's a clear model. There's suggested defenses. It's nice that the safety and security analysis are integrated into the same model. There's missions. It's a mission-centric model so that it's clearly aligned toward a specific mission and easy to understand. And then there's traditional kinds of feedback and also some formal verification. So for our example that I'm going to talk about today, I'm going to use this delivery drone. And the delivery drone scenario is you've got a truck and it's got multiple delivery drones, and it pulls into an area, and then the drone takes the package the last mile. So the key components, architectural components in the drone, there's an IMU GPS system that's going to calculate position. There's a navigation function, flight control, flight actuators. There's a delivery planner function. There's a radio, a delivery item mechanism, and there's a camera. And the idea is that the drone will get the address and have a route to go fly, to go drop off the package. And for high value packages, the camera would take a picture of the delivery area and send that information back to the truck to confirm that it's appropriate to make that final delivery. So that's the mission scenario and the architecture of the drone. So the previous picture of the drone was kind of a PowerPoint architecture diagram. Here we show the diagram that we generated in AADL. So in AADL, for each of those major components in the architecture, we define the inputs and the outputs in AADL, similar to the information that you see on the left here. So then the next thing we do is we have to capture the mission, cyber, and safety requirements using our VERDICT Annex. So the VERDICT Annex is a domain-specific language specific to our VERDICT tool, where we can capture mission requirements, safety requirements, and cyber requirements. So as an example of a cyber requirement, we are saying that the drone shall be resilient to the loss of ability to deliver a package to the appropriate location. And that's really measured by the integrity and availability of the actuation output and the integrity and availability of the delivery status. So, and then the severity of that is hazardous. So the consequence of that not happening would be hazardous. And down at the bottom of the chart here, there's a little table. And in aerospace terminology, it's common to use this catastrophic, hazardous, major, minor, and none. And we define the acceptable likelihood of successful attack to be aligned with those different consequences. And then when we implement our defenses, we need to implement the defenses to level A, B, C, D, or E, security design assurance level, in order to line up against the consequence. So if we've got a catastrophic consequence of a cyber requirement, then we need to make sure we've got a design assurance level A defense implemented to prepare for that. So we define our cyber requirements and our safety requirements, and then the mission requirements. So we've got a mission requirement here that says the mission is to deliver a package to the intended location. And in order to satisfy that mission requirement, we need to satisfy cyber requirement 1, 2, and safety requirement 1. So the mission requirement is kind of a hierarchical aggregation of the cyber and safety requirements that we'll actually be calculating. So then we need to go in and set our cyber and safety relations. And that's a matter of aligning the inputs and outputs of each of the components. Now, we can either spell these out explicitly like we've shown here. For example, we've got a cyber relation for the camera out integrity is dependent upon the camera in integrity. So it's kind of a straight pass-through of this simple system. So we have a feature in the tool where you can automatically set all of the outputs of a component to be to have a cyber relation with all of the inputs, or if a designer wants to be more specific, they can set them out specifically for a more refined design. So then we need to set some mandatory properties, and there's really only a handful of properties that you have to set. And if you don't set them, there's default settings, and the default settings are the most conservative. So with all the different properties are captured in this case consolidated properties file. And for each component, we need to go in and set these properties. And these properties are simple embedded system kind of properties. Can that component receive software configuration updates? Can it receive, what type of component is it? Is it hardware? Is it software? Is it a hybrid? Does it have any sensitive information? Is it inside the trusted boundary? What's its pedigree? Is it COTS? Is it something that's been internally developed? So those are relatively simple properties that we set. And then that's it. So then we can go run the tool. So then from the verdict menu, from the menu in OSADI, we select the verdict tool. And then there's a couple of different settings there. And for this analysis, we're just going to run the architectural analysis. And maybe it takes a minute or two, and you receive some feedback inside the OSADI window. And in this case, we can see that we had our cyber requirement 1 and 2 and safety requirement 1 that were required to pass mission requirement 1. And you can see that we failed. And but we passed the safety requirement. That was okay. But we can see those 2 red X's on the cyber requirements. And when we click on that, we can see the information you see down below, and we can see that our delivery item mechanism is vulnerable to KPEC 439, our delivery planner to KPEC 438 and 39. And those are the KPECs that we're still vulnerable to, and we need to put in some defenses. So in the center column there, you can see the defenses that we're recommending, and those defenses are based on our cyber defenses that are verdict properties. And then the suggested defenses in the right-hand column are aligned with the NIST 853 defenses. So we try to provide as much information here in clarity for the user to go in and update their model. And it's localized and very specific. So if the designer wanted to understand more about KPEC 439 or 438, they can go to MITRE's KPEC page and put in the number of KPEC that they want to learn more about. And it pops up a rich display of information and provides outstanding feedback and very clear and very usable. Then as far as our defenses go, you can go to the NIST 853 page, and similarly, you can select the recommended defense that we've talked about. And this page gives you appropriate defenses for low, moderate, and high implementations. So then we go in and for the tool, we can go in and set our cyber defenses that are related to those NIST 800 defenses, and we can set them at different levels. So we can set them basically integer levels, 0, 1, 3, 5, 7, or 9 that align with the A, B, C, D design assurance levels. And then we can rerun the tool once we put in the defenses and put the defense at the appropriate level. And you can see that at that point, we get all the green checks and we pass. Now, what's interesting here is we can move the trust boundaries around. We can move components. You can say a component is COTS or something developed inside. You can make something have software update availability or not. There's lots of different ways you can experiment at the system level and really move that vulnerability around and experiment with different defenses and things. So we have a manual approach. We also have a synthesis approach that automatically generates the lowest cost kind of set of defenses for the system is designed. Our tool is available on our GitHub. We have a GE high assurance team at the research center, and we have all the different tools that we develop as open source. We put out there on this GitHub. And in addition to the tool that you can grab, there's also example models that will run in the tool. There's a wiki page with background information describing how the tool works and tutorials and things like that. The tool's available to run either natively on a Mac, or you can run it in your PC with a Docker support. And it's all right there for you to pull down, and relatively simple installation and operation instructions.
Thanks a lot, Michael, for your talk. That was very interesting, and thanks for the publications. I was about to ask about those. So the tool that you presented has a lot of dependencies on external tools, and that's great just to leverage the existing results from the community. And it illustrates how you can basically just use AADL as a blueprint for your design and connect to those analysis tools. One aspect I would like to ask is, what type of complexity did you experiment when you tried to use AADL to bridge to those tools in your design workflow?
Well, let me see if I can answer that, if I understand it correctly. So, when we first started developing the tool, we liked the idea of using the OSADI environment in AADL, because the OSADI environment provides a lot of baseline, a lot of background capability, and then we could develop just a plugin for our analysis. So we like the idea of having an environment where we could express our AADL models, and then we could focus on our analytic and just build it as a plugin. So we found a lot of value there. When it comes to, and it was relatively easy to build the plugin. There were some examples that we could learn from, and within a few months we were up and running with our plugin. We started off, in terms of the complexity of what we modeled, modeling that delivery drone in a military system that looked somewhat similar to that. And then in GE, we've experimented with some different products, additive machine, engine controller, some wind turbines in wind farms. So we've, I wouldn't say we've gone to the complexity. From the architecture point of view, we stay at a relatively high level. We don't get, one of the issues that we have is when someone says they've got a legacy system and they say we've got this complex set of implemented software. And really our tool is designed to analyze an architecture, so that all the details in the implementation of the software, we need to abstract several layers up to really do our analysis. So that's one of the challenges that we've had. And the complexity of the systems that we've done are, I would say, I'm not sure what the right measure of complexity is, but I would say reasonably complex to be an industrial relevant tool.
Yeah, that's really one of the concern of the AADL community, just to make sure that we're at the right level, not going too deep into the implementation, or not being too abstract, and being at the boundary of CSML. And your talk really illustrates that perfectly. So thanks a lot for your presentation, Michael. It's now time to wrap up for morning, even though it's almost 1 p.m. We'll just let everybody know that we will take a 10-minute break before starting the afternoon session. And thanks again for all speakers today. That was a very great session. A lot of interesting views on the same topic of how to leverage architectural description for the analysis of systems. And we'll continue this afternoon with 2 quick tutorials, one on AADL and one on ACVIP. Thanks a lot.
Thank you.